Welcome to qnawire.
Okay, so we need to give the binding energy of zinc, zinc 64, using the semi-empirical binding energy formula. And that'll give us an estimate of the binding energy for the nucleus. So I'm going to write that formula, and then we'll at least name the terms, and then plug in the numbers and calculate it. So the binding energy using the semi-empirical formula is going to be equal to small a, big V, A. I'll point out right away that A is simply, it's like the mass, not the actual mass, it's just the number of neutrons and protons, right? So Z plus N, which for zinc, that's the 64 that we're interested in, right? That's like the nominal mass, not accounting for the fact that the mass of protons and neutrons is not exactly 1. Okay. Right. Okay. So this first term, little a, V times big A, is the volume term. It's proportional to the volume of the nucleus. Okay. All right. Next, we have the surface term. It's sort of a correction to the volume term based on strong force. Okay. Now we have a Coulomb term. Oops. Let's write this a little more clearly. There we go. Okay. And it's basically just based around the electrostatic repulsion between protons, because you are bringing many positively charged particles into a close proximity. Right now we've got our asymmetry term. Sort of based around the Pauli exclusion principle. I'm not super familiar with the physics behind it. And then finally, we have like a parity or pairing term. Right? This is kind of about how electrons need to be paired. It's let's see, and it's either going to be 1 or 0, depending on the number of neutrons and protons. Okay, so this is the formula. Now, all of these, right? So A, we already said that's just like the nominal mass. Well, these little a terms, all these correction terms, these are empirically determined, right? Through usually through least squares fitting of like actual data, for things like empirically determined data, right? So your mileage may vary. If you've been asked this question, you've likely been given values to use either in your textbook or in supplemental materials. I have got values that I can use, from sources. It just they may not match yours, right? So keep that in mind. Okay. So I'll just put these in here. .8 electron volts. Okay. Then we've got 18.3. So I'm just gonna save the units for the end here. Otherwise, it's not going to fit. right? And then essentially we're either going to get like a positive, a 0, or negative term, okay? And that's going to depend on Z and N, right? So we can figure that out now. So the atomic number for zinc is 30. So we've got N equal to 34. Okay. So in the case that A is even and both Z and N are even, we're going to get a positive value out of our pairing term. Sorry, right? So we're going to get plus delta Kronecker 0, right? And then the actual value that we're going to get for that is going to, it depends again on where your data comes from, for these empirical values. But the form I'm going to use is 12 over a to the 1/2, right? But there's also, this can also be represented as 34 over a to the 3/4, right? But it depends on which data set these empirical values have been derived from, or what methods it's been used to fit the empirical data. So again, we know that it's positive because of the evenness of A combined with the evenness of Z and N. But what value we actually use for the delta Kronecker 0 is really depends on what data you've been given. Okay. From here on out, it's just tabulating. So I'm going to pause the video and do this off to the side. Okay. And the final answer that I got, again, use your own data and do your own computation, just in case, is 558.805. Okay. So that's pretty close to the, tabulated binding energy, right, that we were given in the problem. That's very close.